Welcome to the 12th lecture from chapter number 7. We are studying VLSI design, and in this lecture we are going to perform DC analysis of a NAND2 circuit. In the last lecture we studied how to implement the CMOS structure or the CMOS schematic of a NAND2 using equal number of PMOS and NMOS transistors. In this lecture and in one of our previous lectures we also studied that DC analysis means that we apply all the voltages from logic 0 to logic 1, and we'll apply all the voltages from logic 0 and logic 1, and we'll observe the output Vout, and we finally draw a plot between the in and output and call it VTC. And we also studied finding a numerical expression for Vm, the middle voltage for which Vin is equal to Vout. Right, in this lecture we'll numerically find Vm for this NAND2 circuit that we implemented last time, starting from a Boolean expression. Right, in the PMOS structure, in the PMOS array, we have two PMOS transistors connected in parallel, and in the NMOS array we have two NMOS transistors connected in series. Let's see how this affect the Vm. Previously we have calculated studied Vm for previously we have been studying Vm for a CMOS node. In this lecture, let's see how we can implement Vm for this NAND2. In NAND2 we have PMOS, two PMOS transistors connected in parallel. This means if they are in parallel, the Rp, the equivalent resistance of the two, would be half, because we know that the resistance turns to half if we have two resistors of equal values of resistance connected in parallel. And Rp is 1 over beta p. This is what we studied in one of our previous lectures. This means Rp is inversely proportional to beta p. So if we have the equivalent Rp is the Rp of an individual transistor divided by 2, this means beta p should be double, because beta p is inversely proportional to Rp. Alright, we can perform a similar analysis for the two series connected NMOS transistors, these two transistors. Right, the individual beta is beta n for the two transistors, and they're connected in series. This means the resistance would be double. Rn is equal to 2 times the individual resistance. This means beta n is turned to half, because beta is inversely proportional to resistance. Right, and we have also studied expressions for finding ID. So if we assume this to be one transistor having this beta p, and this combination to be one transistor having this beta n, we can write the expressions IDN and IDP like this. IDN is this beta n divided by 2 VDD Vm minus VDN squared, and for IDP this beta capital P divided by 2 VDD minus Vm minus VDP this whole squared. Right, and we studied that when we apply Vm as the input, the output is Vm, and we have the same current flowing through both transistors. So therefore, at Vm, IDN is equal to IDP. This is we studied when we studied CMOS node. Right, so beta n divided by 2 Vm minus Vdn squared is beta p divided by 2 Vdd minus Vdm squared. Right, this beta n is beta n by 2, and this beta p we studied, this is 2 times beta p. If this 2 cancels with this 2 and we divide this here, it becomes beta n divided by 4 times beta p. minus VTN squared is VDD minus VM minus VTP squared. And then we can compute square root on both sides. And we can multiply this with VM, the same that we have done before in case of a NOT. Right. And then we can join or combine the terms containing VM to find, and if we take this, it can also be written as 1 over 2 because square root of 1 over 4 is 1 over 2, is VM. This is plus 1 is whole and VM. I've taken this VM on this side of the equation. And this is minus. Right. And we can take this on the other side. This means this is VDD minus VTP plus beta N over beta P to VTN. And if we divide it here, this becomes 1 over 2 square root of beta N over beta P. Right. So this is an expression for a 2-input NAND. The VM, the expression for the middle voltage for a 2-input NAND. And if we have, this is for a NAND2, a 2-input NAND. What should be the expression for NAND3? Of course, that would be 1 over 3. 1 over 3. Everything else would remain the same. You can check that and you can go through the whole process we have went through. And what is the expression of VM if we have NAND N? NAND N. If we have an N input NAND, that of course would be 1 over N. Right. That's all for this lecture. In the next lecture, we'll derive a similar expression for NOR 2, NOR 3, and NOR N. And then we'll move to the transient analysis for more complex logic circuits, just implemented using CMOS. Thank you.